Good morning and welcome back to the second section of Chapter 12. In this section, we're going to have an introduction to series and summation notation. Last time we had an introduction to sequences, and then afterwards we'll be looking at both of these together because they're definitely related to each other. So, first of all, our learning targets. And by learning targets, I mean learning target. I can evaluate the sum of a series expressed in sigma notation. And so, we might be thinking, what is a series? And that's a very good question. I'm glad you asked. So a series is kind of like a sequence, except instead of the numbers being separated by commas, they're being separated by addition signs. It's the sum of the terms of a sequence. So for example, 3 plus 5 plus 7 plus 9 plus 11 plus ... Now that is one of the types of series we have, and that's called an infinite sum, an infinite series. We also have a partial sum. And a partial sum is what we're going to be looking at today, where we're not going to take ... We'll be just adding up the first however many terms. Infinite sums are a little bit trickier, and we'll be looking at those in Section 5 next week. So that's what a series is. It's just the sum of a sequence or part of a sequence. And so, but to use this, we use what's called summation notation. And that's going to use that big capital sigma that we saw a little bit last chapter. We're going to see a little bit more of it this chapter. Generally speaking, a summation, a sum, a series, isn't going to be A sub n. A is for a sequence. It's going to be S sub n. S would stand for sum. So S sub n equals, and we're going to use a big sigma, and it's going to have other pieces. So the sigma means we're just going to add a bunch of stuff together. Other than that, we have a starting term down here at the bottom. We're going to start with term 1. A lot of times we use k. We don't have to. But so we have k equals 1. So we're going to plug in 1. So right now we have 2k, so that'll be 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus all the way up to the number at the top, which is the ending term. In this case, it's a generic n. So we'd go up, we'd have 2 times 1 plus 2 times 2 plus 2 times 3 plus ... 2 times n. And then this piece here, this 2k, that's just going to be an explicit formula. So you can't use recursive formula here. That doesn't work. It does have to be explicit. And again, that's just like what we've been seeing for the past few years. F of x equals something. We have k instead of x. That's the only difference. So this is what summation notation looks like. We're going to be doing two things with it. We're going to be going from this to find the sum, and we're also going to be putting it into summation notation. So to find a sum, we can have our summation. We have k equals 1 to 4 of k minus 1 over k plus 1. And I tried to get one that's a little bit trickier here. So we're just going to start by plugging in 1. So 1 minus 1 is 0 over 1 plus 1 is 2. Plus, plug in 2. 2 minus 1 is 1 over 2 plus 1 is 3. Plus, plug in 3. Plus, plug in 4. And that's it. We're going from 1 to 4. Then we just have to add these numbers together. So, well, this one's 0, so that's easy. 1/3 plus 1/2 plus 3/5 is 43/30, or probably 1.43 repeating, is my guess how you would write that. But we just find the sum, and we just add them together. And so that's all it is for finding the sum. If we want to write it in summation notation, we're going to have to find an explicit formula, which is what we did yesterday a few times, and then figure out how many terms we need. So if we have something like this, 1.1 plus 2.2 plus 3.3 plus 4.4 plus 5.5, we need to find an explicit formula. So how do we get from 1 to 1.1, 2 to 2.2, 3 to 3.3, 4 to 4.4, 5 to 5.5? We multiply by 1.1. It's just 1.1n. And that's our explicit formula. I used n instead of k. It doesn't make a difference. Then we need our summation notation. We're going from the first term. I would always start with the first term. 2, we have 5 terms. We're going to the 5th term. What happened? There we go. Summation notation, we're going from the first term to the fifth term of 1.1n. And that would just be writing this in summation notation. We don't have to do anything with it. That's all we have to do. Notice since I used the n variable, I used n down here instead of k. It's just a little notation. So let's look at another one. 25 plus 24 plus 23 plus 22 plus ... plus 1. Well, we know we're going to have 25 terms, right? Because 1 all up to 25. So we're going to go from k equals 1 to 25. And we need to figure out the equation. I know a lot of people, they see it's 25 minus 1, or 25 minus k. Well, if we start that, 25 minus 1 is 24. So what do we have to start with to subtract 1 to get to 25? Aha, 26 minus k. And that's all that is. You could have gone 25 minus k and then gone from the 0th to the 24th term. But again, I'd usually start with k equals 1. It just makes things easier. All right? Well, that's what the notation is. So now let's look at some formulas. And apparently I forgot to fade some of these in. We have some formulas. In fact, it's not only some formulas. We're going to look at some sum formulas. Because how often do you get to say some formulas? The first one is the constant series. The constant series is when we add the same number up a bunch of times. Like 4 plus 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 4. If you wanted to figure out what this was, would you actually add all these? What's a shortcut for a bunch of addition? Multiplication. And that's what it is. You'd say, hey, I have 4 however many times. It's that number times 4. And so the sum of a number, c is a constant, from k equals 1 to n, is just how many of them did we have times the number, n times c. A linear series, which is the one we have next, is when you have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus blah, 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 up to a number. We'll branch out from this a little bit on Thursday, but we'll be looking at this type of thing. And we'll see that the rules still actually, they still hold. But this one, and there's a cool story that goes along with this I could tell you in class, but I'm not going to take the time in the video. What happens is if you take the first one plus the last one, you get 101. If you take the next one plus the next last one, 2 plus 99, you get 101. 3 plus 98 is 101. 4 plus 97 is 101. So when you take these pairs and add them together, you always get 101. And then we just have to multiply by how many pairs we have. That's going to be half of the number. So it's however many numbers we have, 100, divided by 2 times 101, the first plus the last. In general, so we have the sum of k from 1 to n. It's n plus 1, the last number plus the first one, times how many numbers we have divided by 2. And then the last one we have is a quadratic series. That would be if we just have the squared 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus however many squareds we want. And this one, there's no really great way of looking at it. There's the equation, the sum for k squared. It's going to be n times n plus 1, just like up here, times 2n plus 1 divided by 6. I would not expect you to remember this one on a test. I would give this one to you. These ones you can actually figure out pretty easily, and we're going to be using this one in a more generic form quite a bit. So you'll know this one pretty easily. But I would not expect you to remember this one, the quadratic one. There's no reason for that. But we just plug it in. So here, 1 plus 4 plus 9, so it's 7 is our n. 7 times 7 plus 1 times 14 plus 1, and then divide by 6, and we get the same thing as if we added all these together. This could be derived for you, but it's not pleasant, and it will not help with your understanding, most likely. Anyway, that would be section 2. So I hope you took notes, post a comment, and I will see you in class.